Hello and welcome back. So today is the third day of the 6th week of this course. So in the last few lectures we learned about different types of lasers and laser mediums and certain properties of those. So now we are in a condition that with those basic knowledge that we acquired in last few classes, we can now look at the applications of lasers. Okay, and in this case, in this particular section, we will learn few applications in detail and some other in a brief manner. Applications, we mentioned about several applications. So one of the finest application of laser lies in the field of nonlinear optics, and that will be our first topic of discussion. So during the days when a laser was being developed, in those days people needed to use several different colors, different frequencies for various research work or applications, other kind of commercial applications. Now converting the frequencies was not so easy. What I mean is like developing a laser source having the particular wavelength of interest was not so straightforward. So in those days the frequency conversion used to earlier be done in a window where a dye could be operative, that means using dye laser. So if we consider one was using dye laser, but that was also quite limited based on the dyes available and the characterizations of the dyes at that particular time. But one most used frequency conversion method was based upon using some material which are called nonlinear optical material, and particularly the crystals made up of certain material which are known as nonlinear optical materials. Now I will give you one particular example to make it little clear to you. So suppose we have one India laser. So let us consider India laser. So the fundamental frequency, which is the most common fundamental frequency of India laser, as we know, is 1064 nanometer. That is the fundamental. Okay, why we are calling it fundamental and all these things, it will be pretty much clear. So essentially, whenever we deal with any laser frequency, directly coming out of the laser cavity is called its fundamental wavelength. Okay, so that is directly related to the active medium and its properties. So now what people used to do, they used to take the output of India laser, which is say given by this particular color, and then you put transparent crystal of something like beta barium borate. Okay. So, now when the light used to pass through this one under certain condition, under certain angle and all, one can get several different frequencies, right. So, one of course, if you are passing the light through the medium, then it can just pass through as it is. So, one will get back the 1064 nanometer light unperturbed. But there were several other wavelengths, and these wavelengths which used to come out of this crystal is not arbitrary. Okay. So, one main wavelength that used to come out was at 532 nanometer. Okay. Then there was light at 355 nanometer, and also some light at 266 nanometer. Okay. So, all these different wavelengths that used to be obtained, I mean it will always give rise to these different sets of wavelength, and also beyond when an intense laser light passes through this kind of crystal, which we took as beta barium borate. Now, this conversion is not arbitrary. If you look at, you can see that this 532 nanometer is exactly the half of this wavelength 1064. 266 nanometer is half of 532. 355 is roughly 1/3 of this 1064. So, these are not at all arbitrary. There is a very finite relation between a starting wavelength and the wavelength that you can obtain when you pass through some material which we know as nonlinear optical media. And this type of frequency conversion is obtained from nonlinear optics, and this frequency conversion phenomena is known as nonlinear optical phenomena. We write this nonlinear optics or nonlinear optical term in short as NLO, and very often we will use this term NLO. The first observation of this kind of nonlinear optical frequency conversion was obtained in ruby laser. Okay. So, the first wavelength that one got was like ruby laser has a fundamental wavelength of 694.3 nanometer, and it was converted using a nonlinear optical crystal to 347.15 nanometer. So, this is just a historical fact. Okay. The first frequency conversion through nonlinear optics was obtained at 347.15 for ruby laser, and it converted the fundamental frequency of 694 to 347. Now, whenever these kind of frequency or conversion takes place, what is the advantage? Like, I mean, one can easily think about having just a fluorescence, right? I choose a dye, I get a fluorescence, and fluorescence is redshifted compared to the excitation wavelength. So, I could easily get that frequency conversion, right, choosing a particular dye. So, what is the advantage of this kind of frequency conversion? The advantage lies here is that the properties of a laser light is intact in this particular case. What I mean is, the light that comes out from this nonlinear optical medium is coherent, it has the directionality, and still it has high intensity. So, it possesses all the properties of a laser light. So, this is the fundamental, and whatever the output, that may be harmonic or some other wavelengths, they will be just like laser. So, even though I do not have an active medium which can directly give me this laser wavelength, I can use another laser and use this nonlinear optical material and frequency convert them to achieve just like another laser at another frequency. Okay. Now, we will try to learn rather briefly what is nonlinear optics. So, the question is, what is nonlinear optics? Okay. So, to answer this one, let us first consider what are the properties of a conventional light source. Okay. Because this nonlinear optics, it is related to the intensity of incident light as well also the particular type of material that we are considering. So, if we consider conventional light sources, what are the properties that we have? First place, they are not monochromatic, fine. Also, they are not coherent, right. Also, their intensity is fairly small. How small? We have seen it earlier in one of the earlier classes that the electric field amplitude is something like between 10 to 1000 volt per centimeter. This is fairly a small number. Now, if this intensity of light, okay, for a moment I forget about the other thing, wavelength or the phase. So, if I just consider the intensity of light, this amount of electric field, if it is allowed to interact with some material, okay, so this is a material which we can take as an dielectric, okay, for example. So, what will happen? So, it can give rise to reflection, correct? It can give rise to refraction, it can also give rise to absorption, it can give scattering. Okay. Now, these weak field of these conventional light sources can give rise to these kind of properties, but they can hardly alter the macroscopic or microscopic properties of material. So, this interaction, okay, so this is interaction, so these interaction, so they cannot significantly change the microscopic, say let's macroscopic or microscopic properties of the material. Fine. So, this is true for this conventional light sources, which has a very small intensity in the order of 10 to 1000 volt per centimeter. Okay. Now, at this point, if I ask you, fine, I said that they cannot significantly alter the macroscopic or microscopic properties, but why? Okay. So I am asking why it cannot change the macroscopic or microscopic properties. Okay. So, if it has to, if a light source has to alter the macroscopic or microscopic properties of the material that is interacting with, then it should, the electric field of the light should have an intensity at least comparable to the intensity of the electric field in the matter itself. Okay. So answer, if I say, is that the intensity that is 10 to 1000 volt per centimeter, the typical value is several orders of magnitude less than the intensity of the electric field within the material. What is the typical order of the electric field within the matter? It is typically around 10 power 9 volt per centimeter, and this is 10 to 1000. So, of course, this is like 10 to the power 8 to 10 to the power 6 order of magnitude less. Now, if I have to alter any macroscopic or microscopic property of the matter itself, then I must be able to impart enough electric field to disturb the equilibrium position of the electrons within the matter. The electrons are bound to the nucleus, and you have the associated electric field intensity of this sort. Now, until and unless I can give an input of the order of this number, I cannot change any property of the matter. Now, if you think about the solution, so solution, of course, you need to use very high electric field. When I say very high, that means comparable to this number. Okay. Now, if I consider a laser, what is the typical intensity of a laser? So, if I consider particularly pulse laser, so for pulse laser, the intensity of the laser beam can be much greater than a terawatt per centimeter square. We have done some problems associated to this, and we have seen that I can go much more than this one. Now, these numbers will transform into an electric field intensity. So, this number will be approximately 10 power 6 to 10 power 8 volt per centimeter when I consider the electric field amplitude of the same beam, and I can increase it much more. At least we can focus it and we can increase the intensity. So, I can achieve an electric field amplitude which is comparable to this number. Okay. So, with a laser beam we are in a condition to perturb the equilibrium positions of the subatomic particles within the matter, basically electrons, and that is the key to achieve some responses which are nonlinear functions of the input radiation intensity. Okay. So, now let us consider a weak field. Say we call it E. Okay. So, this weak field, when it interacts with matter, what it will do? It will create an electric induction. So, when it interacts with matter, it will create electric induction. Okay. Or it will induce some electric field, in other words. So, this electric induction, if I call it as T, then this T is equal to the given input E plus the quantity 4 pi to P. Now, there is a new term, this P, which is known as polarization. That is created in the material by this incoming light field E. All right. Now, if it is really a weak field, that means the E is small, what do we have? This, the polarization. So, for small E, this polarization P is proportional to the input electric field intensity E. and I can write equality as this. Okay. This constant chi is known as, so let us call chi 1, this is linear electrical susceptibility. Fine. This is a very important quantity. Okay. We will talk about this one a little bit in a while. Okay. Now, this is a nice expression that polarization is related to the electric field. Now, from where does it arise? So, the origin of this relation that we need to discuss a little bit in order to understand the basics of nonlinear optics, because this polarization and the susceptibility, they are the heart of the nonlinear optics. So, we will stop here today, and in the next class we will start from here, discuss further about nonlinear optics and different orders of nonlinear optics. Thank you very much for your attention.